So, let's talk about string theory. It's famous, or maybe infamous, for telling us the universe has 10 dimensions. But, I mean, look around. We live in a world with 4 dimensions, right? 3 of space, 1 of time. So, how on earth does this theory of everything actually connect to the universe we live in? That's what we're going to dig into, finding our 4 dimensional world inside the wild landscape of string theory. And this is the absolute heart of the mystery, isn't it? It really is like a cosmic detective story. If the fundamental rules of reality need 10 dimensions to even work, but we only ever see 4, what happened to the other 6? Where did they go? Are they just, a mathematical trick? Or could they be hidden somewhere, right under our noses? Well, the leading idea is this brilliant concept called compactification. And it sounds complicated, but there's a really simple way to think about it. Imagine you're looking at a garden hose from super far away. It just looks like a one-dimensional line, right? But as you walk closer, you see it has a second dimension, that little circle you can go around. The idea here is that the extra 6 dimensions are just like that circle. They're curled up into some tiny, intricate shape, way too small for us to ever notice in our day-to-day lives. Now here's the catch. You can't just roll up these extra dimensions any old way. String theory is, well, it's super picky. It has these incredibly strict rules. And one of the biggest ones is all about symmetry. And this rule, this constraint, is our first major clue in this whole investigation. So what's the deal with symmetries? Well, there are 2 kinds that matter here. On one side, you have what's called a global symmetry. Think of it like the pattern on a chessboard. It's there, it's a pattern, but it's kind of just accidental. String theory says, nope, the fundamental laws can't have those. But then you have gauge symmetries, and these are the real deal. They aren't accidental patterns. They are non-negotiable, fundamental requirements of the physics, and each one is directly tied to a physical force. And this quote from the research really nails it. This isn't just a guideline, it's a core law of string theory. And what it's really saying is this: any continuous symmetry you find anywhere in the universe must come with a force. It's a package deal. You can't have one without the other. And that single rule just massively narrows down the possibilities for what a universe can look like. Okay, and this leads us to what is, honestly, one of the most mind-bending and beautiful ideas in all of physics. If every symmetry has to be a force and the symmetries are coming from those hidden dimensions, then that means the shape of those hidden dimensions is what creates the forces we see every day. The geometry of the universe is literally forging reality. Let's just walk through that one more time because it's wild. You start with this blank slate of 10 dimensions. Then you compactify 6 of them. You curl them up into this incredibly complex little shape. And here's the magic part. All the specific twists, turns, and holes in that tiny 6-dimensional shape are what create the gauge symmetries that show up in our world as things like electromagnetism and the nuclear forces. The shape is the physics. That's an absolutely incredible idea. It's so elegant. But you gotta ask, is it actually true? Well, we can test it. See, if the forces we know and love are really just different faces of a single underlying geometry, then at super high energies, they should all merge back together into a single unified force. So it's time to put this beautiful idea on trial and see how it holds up. To run this test, physicists use a kind of cosmic ruler that's measured in energy. And these are the key marks on that ruler. You've got the electroweak scale, which is kind of where we are now. Then there's the hypothetical grand unification, or gut scale, which is where we expect the forces to meet up. And then way, way up there are the scales of string theory and quantum gravity itself. So here's the big test. We can measure how strong the fundamental forces are down here, at the energies we can reach in our labs. The question is, what happens if we trace those strengths, if we extrapolate them all the way up to those ridiculously high energies? Do those lines all converge and meet at a single point? If they do, it's a massive win for unification. And what happened? Well, the result is just stunning. If you just use the particles we know about in the standard model, the lines get close, but no cigar. They miss. But if you add one extra ingredient into the theory, look what happens. They snap into alignment and converge almost perfectly. It's this beautiful, tantalizing near miss. Now, you might hear near miss and think that's a failure. But in physics, something like this is way more exciting than a perfect hit. It's not a mistake. It's a clue. A huge clue. It's the universe telling us, hey, you are so close. You're on the right track, but you're just missing one little piece of the puzzle. So what was that missing ingredient? It's a famous idea called supersymmetry, or SUSY for short. The theory basically says that for every particle we already know, there's a heavier superpartner out there that we haven't discovered yet. And it's the effects of these hypothetical particles that slightly adjust the paths of the forces and make them all converge so beautifully. This near unification is one of the biggest hints we have that supersymmetry might actually be real. So let's just put this all together. String theory gives us a way for forces to be born from geometry. It suggests these forces should unify. Then we add in supersymmetry, and our actual data shows that they do almost perfectly unify. That tiny little gap that's left over between where the forces unify and the even higher energy of gravity, that's the frontier. That's where all the exciting new physics is happening. It might be telling us precisely how supersymmetry is broken in our universe. And that brings us right back to the beginning, to this amazing cosmic mystery. This beautiful, almost perfect picture that string theory paints is a massive achievement. But what does that final tiny gap really mean? Is it a sign that the whole idea is just wrong? Or is it a signpost? A clue left by nature itself, pointing us directly towards the next great discovery in physics?